We're going to shift gears a little bit here now and talk about heavenly motion, motion of planets around the sun, and so on. Now, why are we going to talk about motion of planets and satellites and so on in a circular motion unit? Well, it's because planets, as they go around the sun, go not quite in a circle, but almost in a circle. They experience almost uniform circular motion, as do satellites as they orbit around the Earth and around other planets and so on. So what we're going to do for the last part of this unit is really an application or several applications of uniform circular motion. In order to get you up to speed, though, we're going to give you a little history lesson today, just a short history lesson today. We're going to take you back a couple thousand years, literally about 2,500 years actually, to 500 years before the birth of Christ, to Aristotle. Aristotle looks up in the sky as you would have done in the 4th century BC, as I would have done in the 4th century BC, and quite reasonably concluded that the sun revolves around the earth. We know now that that's not the case. But why do we know now that that's not the case? Because somebody told us, right? Smarter people than us looked up there and said, no, the sun's not going around the earth is going around the sun. You look up in the morning, when I drive into this schoolyard in the morning, the sun is in my eyes because the sun is rising in the east. When I leave here, the sun is in my eyes because the sun is setting in the west. If I look outside the school during the middle of the day, then it's going around from east, around to the south, around to the west. It looks to me like the sun is revolving around the earth. Aristotle, again, in the 4th century BC, quite reasonably thought that the earth is the center of the universe, that the sun and everything else revolves around the earth. We know that's not right, but we know that's not right not because we figured it out ourselves, not because we're smarter than Aristotle necessarily, but because somebody else figured it out and told us. The geocentric theory, geo means earth, earth-centered theory. The earth is the center of the universe, and everything else, the sun and all the planets, revolve around the earth in circles. By the way, that was Aristotle in the 4th century BC, about 2,500 years ago. And then we're talking about 2,000 years ago, 1,900 years ago. A guy named Ptolemy kind of just reinforced that or went a little bit further with that the geocentric theory, the earth is the center of the universe. Let's zoom forward now a couple thousand years to the 16th century. Copernicus. He says, wait a second. Maybe the earth isn't the center of the universe. Maybe this whole geocentric theory, earth-centered theory, isn't right. Maybe the sun is the center of our solar system, and all the planets, including the earth, revolve around the sun. Now, after all, we do look up in the sky, we see the sun rising in the east and setting in the west. It goes around south or east, southeast, south, southwest, west, but we don't see it going around to the north, right? We don't see the sun up there. So maybe this whole geocentric theory where the earth is the center of the universe and the sun is going around the earth isn't right because it doesn't explain everything. Heliocentric theory says the sun is the center and everything revolves around the sun. Helio means sun, by the way, sun-centered. Now, this is what we currently believe, right? This is what we currently know to be the case, that the Earth revolves around the sun and so do all the other planets revolve around the sun. Now, why do we know that? Because Copernicus, 500 years ago almost, told us. If nobody told us, hey, listen, if a 3-year-old looks up into the sky and is asked to tell us what's happening, he's going to say, well, the sun is moving, right? He sees the sun moving from one position to another. We know that it can appear as if one thing is moving when the other thing is moving because it's relative motion. So we know that this this is possible. Let's fast forward a little bit further, another 50 years-ish, to a guy named Tycho Brahe. This guy's kind of an interesting guy. Late 1500s, he made some observations of the planets with an assistant, Kepler. And this is a really big guy, Kepler, his assistant. We'll tell you why in just a few minutes. But bottom line is he looked up in the sky and he measured times and angles and positions of planets and stars and so on and so on and so on. Didn't really do anything with that. Didn't really do an analysis with it. Just took a whole bunch of data. And that data was pretty useful. It was used by his assistant Kepler to come up with some laws that describe the motion of the planets. But he himself didn't do anything with it. Tycho Brahe's assistant, Johann Kepler, he's the guy that really did the heavy-duty analysis with the data that him and his boss, Tycho Brahe, came up with. Tycho Brahe dies, and Kepler uses this data to come up with 3 laws that describe the motion of the planets. This should say, there's a typo here, actually. It should say how they move rather than why they move as they do. Johann Kepler never figured out why the planets do what they do. He just figured out this is what they do. Well, let's go into a little bit more detail on this Kepler guy. Talk about his 3 laws. The first law is what we call the law of elliptical orbits. Now, hold on before you write this, okay? Let me explain what's going on with this law of elliptical orbits before you write it and start copying the diagram drawing, because really, when you write something down, it should make sense to you. We want it to make sense to you. And when you look at this picture right now, this is going to make no sense to you. We get a picture of an ellipse or an egg shape with 2 suns. Do we have 2 suns? No, we don't. So listen carefully to what this law says. Let me clarify a little bit, and then I'll give you time to write this down. The law of elliptical orbits says the Earth, and all other planets as well, so I'm going to say planets, but that means all of them, including the Earth, orbit around the sun in an elliptical path. So an ellipse is like a circle that's stretched out. Now, it's not nearly as pronounced as I have it drawn here. I just have a really pronounced ellipse drawn here so that you remember that it is an ellipse, not a circle. If I was to draw it more to scale, then it would be much, much closer to a circle than what you see here. The Earth and all the planets revolve around the sun in an elliptical path with the sun at one of the focal points of the ellipse. When you have an ellipse, there are 2 points that we call focal points, one at either end. The sun has got to be at one of those 2 focal points. Now, we're not suggesting that the sun is in both places, 2 places at the same time. We're not suggesting that the sun moves back and forth between one position and the other position. We're suggesting that the Earth, or whatever planet we're talking about, revolves around the sun like this, in this elliptical path, and the sun is either here or it's here. Now, the sun doesn't decide where to be based on the path of the Earth. Rather, the Earth decides where to be based on where the sun is. I'll come back to this page in just a second, but I just want to redraw it slightly differently here. Okay, let's say the sun is right here. Okay, the sun is where it is. And then the Earth and the other planets revolve around that sun in an elliptical path. So we could say that the Earth could go around the sun like this. That's an ellipse, and the sun is at one of the focal points of the ellipse, right? That works. So the Earth could go around the sun like that, but the Earth could also go around the sun like this. This time, the sun is exactly in the same position as it was before. The Earth is still going in an ellipse around the sun. The sun is at one of the two focal points, but it's the other focal point. The sun hasn't changed positions. The Earth isn't changing positions either. We're just saying, look, we have that option or the previous option for where the Earth could revolve around the sun. Does that make sense? So we go back to this diagram. The Earth is going around the sun in an elliptical path. It could be such that the sun is at this focal point, or it could be this one, but it certainly wouldn't be both, and it's certainly not going to change positions. All right, here's the second law. Here's one where you really want to wait to write this down until you understand what's going on. What the heck is this picture here? Well, let's label this a little bit better first here. Let's say that the sun is right here, okay, at one of the focal points of this ellipse. Remember, this is an elongated ellipse. It's more pronounced than it really is. Okay, it's not drawn to scale. It's just done this way to illustrate that it's not a circle. Let's say that at one point in the Earth's revolution around the sun, that it's at this position. Now, let's fast forward in time a little bit. Let's say maybe a month. Could be 3 months. It could be 2 days. It doesn't really matter. But we're going to define a time, T1. We'll make it a month. Okay? Fast forward a month. The Earth is going to be over here, right? The Earth goes around the sun, and of course, a month later, or whatever T1 is, it's in a different position. During that time, T1, there's going to be a certain area in here that's swept out. So if we draw a line that joins the sun to the Earth, that line will sweep out an area in here during a certain amount of time, T1. Make sense? Don't ask me how to calculate that area. That's a crazy geometric shape. I have no idea how we'd calculate the area of that shape. But you know that there is an area. So it's just a matter of knowing enough mathematics to find the area of that shape. Okay, I don't know how to do it, but it doesn't matter. We know that there's a certain area there. Let's assume that we're all smart enough to figure out what that area is. Let's fast forward another, 6 months. Now the Earth is way the heck over here. There's still a line that joins the sun to the Earth. And if we zoom forward in time a little bit more, let's say another month, a certain time T2, then the Earth is again in another position. That red line that joins the sun to the Earth has swept out another area in here. We're calling it A2. Here's the thing. If T1 equals T2, in other words, if the time is the same, then the area that's swept out by the line that joins the Earth to the sun is the same as well. So in other words, if T1 equals T2, then area 1 equals area 2. This area is the same as this area, right? This is narrow and high. This is short and fat. Combined, okay, they give me the same areas. That is, if this time is a month and this time is a month, or this time is 3 days and this time is 3 days, then these two areas that swept out by that red line are going to be exactly the same. Now, why do we care about that? Who cares if the areas are the same? That seems like kind of just a neat mathematical trick. Well, it has a pretty big implication, actually. If these two times are the same, if these two areas, I should say, are the same, then clearly the time that it takes to go from this position, or the distance, I should say, that's covered during this amount of time is going to be bigger here than it is here. So the time is the same, but the distance traveled is different. What do we know about the speed of the Earth as it revolves around the sun right here during T1 versus T2? Jonah? Yeah. It's going faster because? Yeah. Yeah, absolutely. It's closer to the sun. It's going faster. So as the Earth goes around like this, and this is the same for all other planets as well, as it goes around like this, it speeds up over here. It has to cover more distance in the same amount of time. So it slows down, covers just a little bit of distance in that amount of time, 1 month or whatever. Then it speeds up, covers more distance in the month, slows down, covers less distance, and so on. So the speed of the Earth changes as it goes around the sun. Okay, it means that the closer the Earth is to the sun, or the closer any planet is to the sun, the faster it moves. Now again, it's not as pronounced as we have drawn here, but the effect is there nonetheless. All right, finally the third law here, called the law of periods. The law of periods says this: the square of the period of revolution of a planet around the sun. In other words, if you square the time that it takes a planet to go around the sun, the Earth takes 365 and a quarter days to go around the sun. Okay, that's the period, the time for one complete revolution around the sun. If you square that period for any planet, it will be proportional to or related to the cube of the radius of revolution. Now the radius changes, right? Because it goes in an ellipse. That radius would be the average radius of revolution. In other words, if we turn this into an equation, right, t squared is related to r cubed. T squared would be equal to a constant times r cubed. Now what we like to do here is rearrange this to solve for that constant, t squared over r cubed. This constant is what we call Kepler's constant. And what's neat about this is that Kepler's, everything that is revolved around, we'll call it a central body. Every central body has a unique Kepler's constant. But it's the same no matter what's revolving around it. So for instance, if we look at the sun, there's a certain Kepler's constant. I don't know what the value is off the top of my head. It doesn't matter. Okay? Kepler's constant for the sun will be the same whether we use data for the Earth revolving around the sun or whether we use data for Mars revolving around the sun or whether we use data for Jupiter revolving around the sun. It doesn't matter. Whatever it is that's revolving around the sun has the same ratio of the square of the period to the cube of the radius of revolution. Now, if we look at some other miscellaneous star, then there's a completely different Kepler's constant. We could say Kepler's constant for the other miscellaneous star would be t squared over r cubed for planet number 1 revolving around it. But it would be t squared over r cubed for planet number 2 revolving around it, and so on and so on and so on. So this Kepler's constant is the same for our sun no matter what's revolving around it, but it's different than the Kepler's constant for miscellaneous star that has other planets revolving around it. Okay, why is that important? Well, knowing this, we can use data from one planet to deduce something about another planet. What's the radius of Mars's revolution around the sun? Well, if we know t for Earth and r for Earth and how long it takes Mars to go around the sun, then we can calculate the radius of revolution for Mars without actually measuring it. So it's a pretty big deal here, right? We can deduce information about one planet based on information about another planet.